Hi, everybody. Next speaker is Liang Yu from Nanjing University. The topic is some applications of recursion theory. Let's welcome.
Thanks for the invitation. And my talk is about some application of recursion theory. And I just because I think many of you are not logicians, so just review some background of recursion theory and how it can be related to analysis. So, every continuous function like f in the information theoretically, actually it can be or the recursion theory you can view it as a reduction, like you can get the information of y from x via this f, and so every continuous function can be viewed as a recursive function or computable function, and even but if f is Lipschitz computation, it's even better. It can keep the Kolmogorov complexity. So if you know the x information of x, then you totally know the information of y, and even restrict to any finite path. And so this is kind of how it related the analysis from between the analysis and the recursion theory, and but this is not exactly true, and because we know there are only count many recursive functions, but there are count many continuous functions. So the relation is every continuous function can be viewed as relativized computable function or recursive function. It means for any continuous function, you can find some oracle Z such that actually is kind of relativization of recursive function relative to oracle Z, or you using oracle Z to compute this function, continuous function. So, and this is not a brand new idea. It can be traced back to Kleene or Addison, and it's very long. It was a very long time ago, but it's a very fruitful idea, and we will see how it can be used to solve some questions in analysis. Okay. So what should okay, whatever. Yeah. Strange. Okay. Let's say. I need to review some high recursion. The so-called high recursion is the usual recursion. The classical recursion is about the time and the space are limited to natural numbers. But for the high recursion, you can have many steps like ordinals. So I don't know what happened here. Yeah, this is okay. Let me use this maybe. This is good. Okay. Whatever. But okay, I just use this. Okay. Okay, and omega 1 ck. So is the least non-recursive ordinal. A recursive ordinal is an ordinal can be presented by a recursive way. You can use a define a recursive ordering over natural numbers, such as the order type is alpha. Then it's called or you can also just find shit or whatever. You can find a recursive. You can find a recursive presentation of omega, which is a Y order, and it's isomorphic to such ordinal. Then such ordinal is called a recursive ordinal. But there are only countable many such ordinals, so there's an upper bound. And the least upper bound is also a countable ordinal. It's called omega 1 ck. And it's C means Church, K means Kleene. And you can also relativize such ordinal to oracle X, so you can get omega 1x, the X recursive ordinal. And Kleene O is a pi 1 complete set of ordinal notations. And it's pi 1 complete, that means every pi 1 set can be computed by such pi 1 set. This is the most powerful pi 1 set. A pi 1 set is okay. It's if you analyze it, maybe you know what is analytic set or project. Okay, how to say it? The analytic set. The complement of analytic set called a pi 1 set, or you can call it a co-analytic set. And this Kleene O is the most powerful pi 1 set. And also we can define Turing jump or Turing degrees. I didn't define the what is Turing jump, but it's kind of halting problems. You can iterate a halting problem is a famous unsolvable problem, and you can iterate this kind of halting problem. Like if you know halting problems, use halting problems as oracle, you can get another halting problem by using this oracle. And so you can have 0 jump, 0 double jump, 0 3 jump, and you can do it transfinitely. But for the transfinite, you need to be very careful because it depends on the representations of ordinals. It might, but it can be proved it doesn't depend on if alpha is recursive. So hyperarithmetic real is a real recursive in some 0 to the alpha. And it's a kind of Borel set. Hyperarithmetic real is a kind of light phase Borel set. So the recursion theory. Kleene proved a famous result, delta 1 equal to hype. In analysis, it's called something like if a set of reals is analytic and co-analytic, then it must be Borel. And this light phase version, and delta 1 equal to hype. And then there's a very nice theorem proved by Sparks and Gandhi. That it builds some very deep relation between co-analytic set and the recursion theory. So a set of reals is pi 1, 1. Then actually it's a recursive enumerable set over some inner model. The inner model L is God's constructible universe. It's a very nice universe of CFC, but a fragment of CFC. And so this theory said a set of reals is pi 1. Then it can be viewed as a recursive enumerable set. So then we can use recursion theory to do analysis. So it's open the door between the recursion theory and the real analysis. And I need some basic theorem. So analysis set is a very nice set. If you know much about real analysis, then actually sigma 1 or analytic set behaves like a Borel set, and it has a very nice property. It's measurable, has a perfect set property, and many results in analysis about the Borel set can be shifted to analytic set. And if A is a countable sigma 1 set of reals, then every member of A is delta 1, 1. That means if you are simple sigma 1 set or analytic set, then you can only contain very simple members. All the members are delta 1, 1. Okay, now we need to review some randomness notion. Randomness, okay, what is a random real? Random real can be defined in many ways using Martin-Lopez test, using Kolmogorov complexity, or using martingales. We just use the simplest way, using not Markov test, or just avoid some kind of null set. In real is random if it can avoid a certain null set. Say R is delta 1 1 random if it does not belong to any delta 1 1 null set. The light phase Borel null set. And Sachs, he proved some very interesting result, and actually they are very important. And if R is delta 1 1 all random, then it does not compute very long ordinals. So this kind of thing says if you are very random, then you are powerless. So random reals contain lots of information, but actually this information is no order, is powerless. They are useless. This kind of thing just says this facts. So if you are sufficiently random, then you are useless. So you contain lots of information, but this information are useless. And another technical result is if you are light phase analytic set null set, then it can be covered by a delta 1 1 null set. Usually, for the boldface case, it's trivial because every null set can be covered by a G delta set, G delta null set. But the problem is you need to be covered by an effective way or definable way. So not every set or not every null set has such property. And but sigma 1 null set has a very nice property. If it's null, then it can be covered by a delta 1 1 null set. So it's an effective way to be covered. And there are kind of many kinds of randomness notion. You can also define real is closed random if it does not belong to closed null set, like a contour set, null contour set. And there are many closed sets. They are uncountable, but it's still null. And if you don't belong any Python 1 or effective closed null set, it's called closed random. Of course, such reals have major 1 because they are countable many Python 1 null set. And Joanna and Frank Stefan, they prove if X is closed random and Y is X closed random, the join is also closed random. It's kind of one Labang theory. It says if you are random and Y is also relative to X random, the XO plus Y is also closed random. So if you random mutually, then join is random. So but the closed random behaves very badly. For example, for any real X and Y is to the above X jump, the holding problem relative to X, then you can find the closed random has the same power as Y. So closed random can be very powerful, no matter how strong it is. And the closed random can be very powerful. So this is not a real randomness notion, but technically. But this notion is useful. We will see later. And there's another theorem called Martin's theorem. These are just basic facts from recursion I will use later. If A is uncountable delta 1 1 set of reals, then it ranges over up cone of cleanest O. That means every real compute cleanest O. Then you can find the member in A such that they have the same power. Yeah. So this is from purely recursion theory. Then we will see how to apply it to analysis. Now it's analysis notion. Losing n property. Losing n property is a function on reals has losing n property if it maps a null set to a null set. So it maps a measurable set to measurable set. And so a continuous function has a losing property if only if it maps null set to a null set. Maps a measurable set to measurable if only if it maps null set to a null set. And there's information theoretical interpretation of such property because null set real does not belong to a real belongs to null set, it means it's not random. So that means it maps non-random real to non-random real. Or reversely, if the image is random, then the pre-image, if image is random, then pre-image must be random. Because if the pre-image is not random, then covered by null set, then the image must also be covered by such null set. Then it cannot be random. So this just says loose sample means it does not increase the randomness strength. So if you are the image random, then pre-image is already random. But we have Pauli, Arnold Pauli, and what's to trick Linda. We have some result to give us strength how is what how to say it's random using randomness theory. So for any if delta 1 x random, then pre-image if for any x and delta 1 x random area R, then the pre-image contains delta 1 x random real. So it means if R is already the image of R is already delta 1 x random, then the pre-image is already delta 1 x random. So in the delta 1 random sense, it does not decreasing, it does not increase the randomness notion. Now we have such a nice theorem for the Luthian property and proved by Banach. If f is continuous and has a Luthian property, then for almost every real R, the pre-image of R is countable. It was proved by Banach many years ago, and of course, many years ago, and then it generalized by some mathematician from Russian school and discrete set theory, Loville. If f is has a property m or Luthian property and measurable, then this also holds. Now we can have a information theoretical proof of such. And I just skip the technical details, but I tell you how to prove it using information theory. So for almost every real means give a function, recursive function. Why we talk about recursive? Because we just can relativize to for a continuous function can be viewed as a recursive function and modulus relativization. So we can just simply say f is a recursive function and has a Luthian property. Then you pick up delta 1 1 all random R. So almost every real is delta 1 1 all random because non-delta 1 1 all random is not. So take any delta 1 1 all random R. Then by the Linda and the Pauli and me, the result due to us, and the pre-image also contains delta 1 1 all random. The delta 1 1 all random only contains delta 1 because it does not increase the randomness. So if image is random, then all the pre-image must be random, must be such random. But the problem is it's so random, so it has no power. It means it does not compute the long ordinals. So omega x equal to omega ck for any such pre-image. But we know it's a recursive function, so it's a kind of can be viewed a reduction. So x must more power than R, and you can relativize Martin's result, and the pre-image f of R is if it's uncountable, then by Martin's result, then it can be actually powerful. So if uncountable, if the pre-image of R is uncountable, and then it must be delta 1 1 relative to R, but everything also compute R. So then by my Martin's it can be actually powerful. Then you get the contradiction. So So then you can get a contradiction because we just proved the preimage must be random, it must be police. But again, but we got a contradiction. If the preimage R is uncountable, then it must be contain an arbitrarily powerful real. So you got a contradiction. So it's a pure information theory proof of such a pure analysis result. And this is for continuous function. Then, but for general result, it's not surprising because measurable. Then you can approximately by losing the result, you can approximate it by a Borel function and actually by continuous function. Then you can prove it. It's not surprising. Also, this argument can be applied in many other situations. Like you can define losing M problem maps not set to a countable set, and you can using information theoretic argument to prove that if F is continuous and the map has property M, so it maps not set to countable set, then F must be constant function. So it must be trivial function if you have losing M problem continuous. Of course, if it's measurable, then the image F is countable. So it's also trivial function. So for losing M problem, you cannot get where the property if you just map not set, not just not set to countable set, then from measurable for continuous or measurable function, they all are trivial. But for general function, yeah, it's very complicated. Now the questions is interesting. So why always we talk about measurable function? Because measurable function has a nice property that can be approximated by continuous function. But how about arbitrary function? So this is open. So it's a function having n property but not having property T2 means for almost every real R, the preimage of R is countable, and while there is a function having losing property but not having property T2. This kind of question has a negative answer under continuous hypothesis, but we don't know whether it can be proved by GFC. So then also can be reduced to a pure recursion theory question, like the uncountable idea of Turing degrees, blah blah blah. But maybe you don't care the part 2. But the part 1 is very interesting, I think. I talked with some analysis, and I told them this question already solved in the case of Borel function or measurable function, and it only remains the case of arbitrary function. The reaction analysis says, oh, it's already solved. They don't care arbitrary function. That becomes a statutory question. It's very interesting. The gap between analysis and statistics. And okay, this is the first application. So I will talk another application. Given a collection of sets of reals, we use sigma A to denote the sigma algebra generated by A. And classical notion of measurable set is Jordan measurable set. A set of reals Jordan measurable if its characteristic function is Riemann integrable. So we use J to denote the Jordan measurable set. So Johnson, a long time ago, proved A belongs to sigma J if only with a Borel set, and F sigma not set A subset of B union sigma, B union X. So it's essentially sigma J. Every member belongs to sigma J is a Borel set modular small set. Such small set is F sigma not set. So the modular small set, every member belongs to sigma is a Borel set. And he asked a question. where does sigma j stand relative to analytic set in 0, 1? So this question also asked by some statisticians like Arnold Miller, and because sigma j is a sigma algebra, so it's just the question essentially asks whether they are equivalent, and but of course they are not equivalent, and because sigma analytic set is not does not form a sigma algebra, and sigma j is a sigma algebra, so they are not equivalent. But the problem is whether every analytic set belongs to sigma j, or you can say co-analytic set to sigma j. So now we give a recursion theory proof for this result, and we build a co-analytic set which does not belong to sigma j, and the set is seen if it has no perfect subset. Like there's the largest perfect since co-analytic set is called C. The light phase one is the light phase one, and such set is countable. It's uncountable under some set theoretic assumptions, but it can be countable if under some wild statistical assumptions. So how large is it depends on the set theory assumptions, but we will get rid of additional set assumptions. We proved firstly by some set theory assumption like V equal to L. So it's very small. It means the set theory universe is very small. Everything is definable, and yeah. So suppose every real is constructible. So the universe of set is very small. Then C does not belong to sigma j. So the complement does not belong to because sigma j is sigma algebra. So the complement of C belongs to sigma j, and then C also belongs to sigma j. So the proof is like this. Okay, suppose C can be decomposed to two sets, a Borel set and a null set, F sigma null set. Then B must be countable. Why? Because it's a Borel subset of C, but C has no perfect subset. So, but we know for Borel set, if it's uncountable, it has a perfect subset. So such Borel set must be countable. So B is countable, and the F is then Cx. Now let's look at the X. So B is countable. That means that constructible universe, and B only in the very low level of this universe, but C can be very high. So X must be very high, in the very high level. So it means X must contain arbitrarily powerful set. But the problem is X is a F sigma null set. So it means it cannot contain arbitrarily closed random real. It cannot contain arbitrarily closed random real. But C can contain arbitrarily closed random by Frank and Joanna and me. And X can contain C can contain arbitrarily powerful closed random. So we got a contradiction because B is countable. X cannot contains very powerful closed random. We got a contradiction because C must contain arbitrarily powerful closed random real. So we get a contradiction. So this is a recursion theory way to prove such analysis result, but under assumption of very strong assumption of such theory. But you can get rid of such some assumption by relativize the proof. So you just define XO plus Y, like this is the boldface version, the relativized version pi on one side. Then you can, by the almost same argument, then you can prove it's a pi on one side, but not does not belong to sigma j. So this is a pure analysis way to prove pure recursion theory to prove analysis result. But we can generalize this and we can prove more general result along this way. So a sigma idea is just idea on the closed on the quantum many union. So it means a collection of very small set. So and the modeling is a discrete set series. And he asked for what sigma ideas one can derive similar result, like Johnson's question. And now we can give a recursion theory a description. How can we define for what kind of sigma idea it is true and under certain set theory assumptions. So a sigma idea, usually we only care the definable nice sigma idea like Borel generated. So Borel generated if it's generated by Borel set. And we have such a result. Suppose our real is constructible. Then for any Borel generated idea, our sigma one side can be approximated by such idea if only if it contains upcode. There is a member contains upcode. So if you can approximate by idea sigma one side, then that means this kind of idea must contain upcode of high degrees. And our analytical set can be also by relative-wise list. So our analytic set can be approximated by AI if only if relative some oracle, then the contains upcode. So we have, but the list is under certain constructible under some certain set theory assumptions. So this is the recursion theory to do analysis, yeah. But this is of course is limited. There are some limitations because we need some set theory assumptions. Okay. Now the third topic is about the geometrical measure theory recently. Okay. It's a very interesting topic. So again. In set theory, and again is okay. Given a set of reals or a set of functions from omega to omega, so there are two guys. They play games. They output the natural numbers mutually, and it depends on the components, the opponents, and so like 1 plays n0, and then 2 plays m0, and then m1, and then m1, and they build a sequence like at n0, m0, like this, and mi, ni. And then we say 1 wins if finally this sequence belongs to A. Otherwise, 2 wins. So the problem is whether you who can win this game, and or whether you have a winning strategy. And like chess. Actually, for any chess, there must be a winning strategy. It can be proven there must be a winning strategy, but we don't know who has the winning strategy and how it behaves is too complicated. We can only prove it exists, but we don't know how it looks like. And so a winning strategy is just strategy. And no matter how the opponent plays, then I can win according to my strategy. So I just give the technical definition. So we say GA is determined if either of the 2 players has a winning strategy. So, so now the question is, for which set A, GA is determined. So this action, surprisingly, this is action, and it states for arbitrary set, either 1 or 2 has a winning strategy. So it's quite surprising. This it can be axiom. And maybe you think, oh, you can easily find a contradiction to build set A neither has a winning challenge. Yes, you are right. And actually, by action choice, you can build a set A. No one has a winning strategy. But the problem is you use action choice. The both have some secret information, like action choice. It states there are secret choice function, and determinant there's a secret winning strategy. So they both contradiction, but they contradict in a non-secret way. So if you remove extra choice, then people believe it's consistent. And Martin proved a very famous result. Even you have excellent choice, you cannot get the contradiction. So if A is a Borel set, then GA is determined. So you can not get the contradiction for nice set like Borel set. Now we will use it to apply it to geometric measure theory. So geometric measure theory is okay. Let's define Hausdorff measure. Hausdorff measure is a kind of out measure. It has no inner measure. It's given arbitrary set. So if you can cover it by a sequence open set and G delta set, and the problem is not the usual diameters. You have D. It's a D. It's a number between 0 and 1. And so you can define. I give this. It's just like a measure, but span and and make it larger, and then then the Hausdorff dimension is the least the infinite of D, such that for such set HDE is 0. So and the packing dimension is the infinite set of PD is 0. It's a kind of okay. I will not review details of geometric theory, just give the definition of the both notations and Hausdorff dimension and packing dimensions. Now we know in the big measure and every measurable set can be submitted by a compact subset. And but how about for the Hausdorff dimensions and whether this or packing dimension, whether this is true, arbitrarily set it has Hausdorff dimension D, then whether you can find a compact set have almost same dimension as this set, and this is not trivial result, and it's proved by Baskovich and Davis. And Baskovich proved it for the hold for sigma 0,3 set, and then Davis observed this technique can be generalized to analytic set. So for any analytic set, the dimension of Hausdorff dimension A can be approximated by its compact subset. It's a highly non-trivial result. And we will prove it by information theory way and information theoretic argument. So K is Kolmogorov complexity, it's prefix-free Kolmogorov complexity. So the effective Hausdorff dimension for a single real, it is fract of K Kolmogorov complexity Y up to n divides n. So is Y up to n means Y every real between 0 and 1 can be expanded as a 0, 1 sequence, infinite sequence. So up to n means up to the n bits, and the Kolmogorov complexity of Y, and the divides n is called the infinite limit is called Hausdorff dimension. And there is very famous result due to roots and the previous roots and is the father of the second roots. And Kiley proved For arbitrary set A, the Hausdorff dimension A can be approximated by the reals below, but the members of A, the effective dimension of members of A. So this is if you know geometric measure theory, if you are real expert of this area, you may know local dimension. Actually, it's kind of state of local dimension, but using information theory interpretation. So and so let's prove such a nice result. And so then it's the opposite door between geometric measure theory and between geometric surgery theory and algorithmic randomness theory or recursion theory. And then Slayman, yes, he gave a talk last year here. Assume V equal to L, and Baskovich-Davis result fails for co-analytic set. So under such assumption, then every sigma one or analytic set, for every analytic set, the Hausdorff dimension can be observed by compiled set. But for co-analytic set, you cannot prove it. No, he doesn't give a canonical example. He just proved it cannot prove it. It cannot be proved. He doesn't give a canonical example. He just proved you cannot prove it for power one set, for co-analytic set. Okay. Now we then but it depends on the assumption of set theory. So but just I told in V equal to L, then there's a wide strong axiom choice. There is a definable choice function. For arbitrary binary relation, you can find a definable choice function. So axiom choice holds in V equal to L in a very strong way. So then how about without axiom choice? And what it behaves like? Now, for example, if AD is true, whether this is whether every power one set or kinetic can be approximated by its compact subset. So now let's give some further knowledge about information theory. So for arbitrary real, this is proved by a bunch of people from Madison School. There are logicians and recursion theorists, and they always write paper together. For any real x, there's a real y low for Hausdorff dimension, but the Turing jump of y computes x. This is just says, okay, what is low for Hausdorff dimension? It just says kind of, it was sort of very unique notion in randomness theory. It's kind of real. It has no power. Even you add it as oracle, then it does not increase information. It does not help you to compute more things. It's called low for Hausdorff dimension. You cannot use y significantly compress information. Usually, if y is a powerful real, then it can be used to compress information. But there are some non-recursive, non-trivial reals. They are not recursive or they are undecidable. They contain some unknown information. But this kind of information are useless. It cannot be used to compress information significantly. It's called of low for Hausdorff dimension. But contradictorily, even though it's powerless in this sense, but the relative, the y jump is a Turing jump, can be arbitrarily powerful. That means even y itself is not powerless, but there's a definable way to find another real from y to get a very powerful real. This is quite unusual because usually people think like if the low forces, the y jump should be also very, very powerless. or if you're using any definable way to get another real, then it should be polished. But no, and they proved there is a real low for hot of dimension, but there's a definable way to find from Y to get a very powerful real. And this was sort of kind of just a technical result, but it turns out to be very useful. Okay, now we can prove actually Baskovich-Davis results for arbitrary set on the X determinants on the AD. So now there is no actual choice. And this just technical. I tell you what's the idea behind this. And so we can assume the hot dot dimension is 1 or it's positive. Okay, and if 0, then of course it's trivial. And by the result we mentioned above, and so there's a kind of function. You can review it as a function, and such that the X jump has dot dimension. CX jump computes a member of A, and this X has effective dimension 1 relative to X. This can confinedly range to 20 degrees. Why? Because just by this result. And it can be arbitrarily powerful. X jump can be arbitrarily powerful, but X is low for dimension. So, but A has positive dimension. So the contains some reals is very complicated. So and then you can build a such set and such that the range 20 degrees confinedly, but the compute X jump can compute a member of a very complicated member. Then actually by AD you have pointed subset. I will skip such a notion. So it reduces to analytic set. So then look at this set C, and it says like some X in P and Phi X jump equal to R. P is a subset of B, but it's perfect. So it's defined with a compact set. And then you produce a set of real analytic set, and there's a subset of A. Then by Baskovich and Davis result, then C can be submitted by its compact subset. So then we proved this. So Baskovich and Davis result hold for arbitrary set of reals. And this result was previously proved by Cron, Fishman, and Jackson by a pure set theory argument. They directly use gain to prove this, and then 1 year later we also find non-proof using information theory. The advantage of their proof is direct way to prove this result, but our argument is flexible, and we can apply this kind of argument in many situations, like Joyce and Price. They proved Baskovich and Davis result holds for packing dimension. So for packing dimension, it's also true. And then by applying this similar argument, then we can prove actually this also true. Holds for arbitrary set under ZF plus AD. But you need the assumption because Salaman's result also holds for packing dimensions. Yeah. So that's it. Thanks.
Okay. Any question? Since there is no questions, thanks, speaker again.
Thanks.